In this video, I want to talk about the definitions and relationships between engineering strain and stress, and true strain, true stress. These are denoted as epsilon, sigma, epsilon t, and sigma t. Normally, if we are talking about strain and stress, we refer to engineering strain and stress because it is very easily derived just from tensile testings. When a workpiece is clamped on one side and the other side, there is an external force F to pull it. The original length of the workpiece we denoted as L0 and has an original cross-section area of A0. And after the tensile loading, it is elongated, obviously, and the length comes to L and the cross-section area becomes A. So for metals, normally the Poisson's ratio is smaller than 1. So this A normally is smaller than A0. So to get the engineering stress, we just divide our external force by the original cross-section area, because these are easily measured by sensors or your rulers, whatever. And engineering strain is the change of length divided by the original length, which is the final length minus the original length divided by L0, which is also denoted by delta L divided by 0. And if we have some transforms, we can see it's L0 of L minus 1. So these values can all be derived very straightforward. So this is very commonly used. If we plot the diagram of the experimental results, we normally get something like this. There is a linear region here, the elastic deformation region. This slope is the Young's modulus, we call it. And we have the yield strength, which is 0.2 offset ys, and the UTS ultimate tensile strength, where after it, the slope of the engineering strain and the stress curve becomes minus than 0, smaller than 0, becomes minus UTS. And this is quite straightforward. For the true stress and true strain, it means the true actual value of this stress and strain. So for true stress, we say it's the external force divided by the actual area, because when you apply this force, the area will change, obviously. So if in the engineering strength, we just ignore the area change, like we just divide it by the original cross-section area. So for the true stress, the area we take it into consideration. So it further equals to this, like A0 divided by what is it? We derive this using the control volume. The volume stays unchanged, and after this UTS point, the necking point, there is necking will happen, but necking barely affects the actual volume of the workpiece. So we just ignore the effect of necking in this part, and we still say that the volume of the workpiece, the rod, equals to the cross-section area times the length. So we say the volume stay unchanged. So this equation comes to F divided by A0 times air minus L0. Right. So this further equals to, if we put engineering stress and strain into this equation, we can use engineering strain and stress to derive this true stress. And with true stress and true strain, we can have a more direct understanding of the change of the properties. So put it down a bit. And the true stress strain curve is normally larger than the engineering curve, like this. It normally doesn't have a down. So the true strain, it is the elongation divided by the origin length. So at each specific time, the length is changing. So like at this point, the length is L, and so this point, if it is elongated by a very small value of delta L, the true strain of this particular time is delta L divided by L. So this L is not L0. It is the actual length of this point instead of the original length. So in the entire process, the length becomes from L0 to L, but the length is elongated. So we need to accumulate this delta L divided by L. So we use an integration from L0 to L, delta L divided by L. So this L is the actual length of every section, every specific time. It is not equals to, it has a different physical meaning or mathematical meaning to this L, which is the final length. This equals to ln L from L0 to L, which equals to ln L minus ln L0 equals to ln L divided by L0, ln 1 plus epsilon. Yes, 1 plus epsilon. Please, ignore it. Okay, so these four are the expressions of engineering strain, engineering stress, true strain, true stress. So after straightforward experiment, we can very soon we can get a value of the engineering stress and strain. These can be derived very straightforward. And normally when we are processing the data, we are modeling the material, we need the true strain and true stress. So we first need to convert the engineering results we get from the testing machines. We need to do this conversion. We put the engineering stress strain to the true stress strain.